Okay. So last time we had a crash course on constructible derived categories and introduced perverse sheaves and classified the irreducible perverse sheaves, so-called Garesky-Macpherson sheaves. The point is that Macpherson and Garesky, they first considered some cohomology theory of non-smooth varieties, and then they realized that these were cohomology with coefficients in some complex of sheaves, and this complex of sheaves was an irreducible perverse sheaf. So Garesky-Macpherson never considered anything apart from irreducible sheaves. The abelian category only was introduced by Belenson-Bernstein-Deligne. So there is some stratum, there is some local system, and then there is this intermediate extension of this local system. Maybe shifted to the negative dimension of the stratum, like this. Okay, so the locally closed embedding of this stratum into the whole thing. And in fact, those are characterized very similarly to arbitrary perverse sheaves, but with more severe restrictions. So that's cohomological. If you remember, for general perverse sheaves, we required that the restriction of a sheaf to some stratum lived, or maybe JS maybe star pullback of this perverse sheaves lives in homological degrees less than or equal to negative dimension of this stratum. Okay, and if I wanted to consider the Schrieg pullback, then it's the same in degrees at least negative dimension of this stratum. Okay, this was the definition from the last time, but now for irreducible perverse sheaves, it is very similar. So you say that first of all, but it's for any S. Yes, and now this irreducible sheaf lives on the particular stratum XS, and then I say that its restriction to this particular stratum XS lives in degree exactly negative dimension of XS. And for any smaller stratum, the restriction to this smaller stratum lives in cohomological degrees strictly less than negative dimension of xt. Then the same for co-restriction. Lives in degrees strictly bigger than negative dimension of X. Okay, so it's just more strict inequalities than in the definition of perversity itself. So if you require something more strict, you obtain irreducible sheaves. Also, you have to require that this local system is irreducible. No, by no means. Then you will just get, by definition, the Goretzky-McPherson extension of this local system. For example, if, say, you have C star embedded into C, and your local system here has monodromy Jordan block. Okay. Then if you take its Goretzky-McPherson extension, it will satisfy those requirements. You see that this L is an extension of a constant sheaf with another copy of the constant sheaf, maybe in degree -1. Well, doesn't matter. Okay, so this thing will have three-step filtration. So it will be the constant sheaf as a subsheaf, then delta function at the origin, then another copy of constant sheaf. Okay, so it will be not semi-simple, but still minimal extension. Okay. So in particular, from the base change and cohomological dimension, if say y or maybe x cubed x is a small resolution of singularities, then the push forward. So in particular, pi is a proper morphism. So the push forward with star and shriek are the same, and if you take the irreducible constant perverse sheaf on the resolution, then this thing is a Goretzky-McPherson sheaf on X. So it's Goretzky-McPherson version of the constant sheaf from open part, open smooth part of X. Okay, so I have this smooth part of X, open embedding into X. Okay, and the most popular example here is the resolution of three-dimensional quadratic cone. So you have matrices of rank 1 of determinant 0. So X is matrices 2 by 2 of determinant equal to 0. Inside matrices 2 by 2, and X tilde is everybody knows what. matrix, and Igor, don't know, maybe, or Vanya. No, so I mean Vanya Ukrainцев, I know. Altan. Just I prompt you to invent a resolution of singularities of this determinantal variety. Some extra data. Matrix and... Huh? No, I mean, no. No, you want to stay geometric. I mean, the trace is... it's a number. It's determined by the matrix A. You need some extra data, something that is not determined by A. In fact, if your matrix is exactly of rank 1, then this is the smooth part of your code. Yeah, it's three-dimensional quadratic code. You only have to resolve at the vertex. Huh? Right, absolutely. Yeah. So there is a line such that AL equals 0, yeah. And then certainly you just glue P1 into this vertex. But if you start from this line, then clearly it's a vector bundle, such that the total space of -1 plus O of -1 over P1.
Значит, можно заметить, что мы можем выбрать линейное пространство, которое соответствует А в четырехмерном пространстве матрицы.
You mean just a line spanned by this matrix A or what? Okay.
Если любая квадрика посреди, она не может пройти.
No, I don't understand. It's in four space. So there's three-dimensional variety. So the if you projectivize it, how to say it? Just proj is two-dimensional quadratic, so it's P1 times P1.
И все-таки там не для всех матриц получается прямая, там есть много получается.
No, if you view it this way, starting from A, then it's then you glue P1 into the vertex of this cone. But if you start from the line...
Я думал, что Ваня говорит про изначальное пространство.
So maybe Vanya says that if you just blow up here, you glue into this singularity P1 times P1. But this will be not a small resolution. Yeah, I didn't even say what is small, but...
you can also construct this resolution by blow. You need to blow up some well divisor.
Right. So you blow up not the maximal ideal of this point, but something smaller. Small means that it is stratified. I mean, its behavior along strata of this singular space is equisingular, so to say, and the dimension of the fiber over any point in a stratum is less than 1/2 of codimension of this stratum in X. And unless this stratum is the open stratum of smooth points. The codimension is 0, and the fiber is also 0-dimensional, so it's not a strong strict inequality. Okay, so in this situation, the whole thing was 3-dimensional, so the codimension of the point was 3, and this 1/2 codimension is 1.5, but dimension was 1, which is strictly smaller than 1.5. Okay, but if you consider the full blow up, then dimension would be 2, but that is bigger than 1.5. So it does not work. Okay, but maybe let me say that there is also a notion of semi-small. Is when this inequality is not strict. And then it results in, like in the comparison of these two definitions, it results in the fact that the push forward of this constant sheaf is perverse. So it's not necessarily irreducible perverse, but just perverse. Okay, and semi-small resolutions are also abundant. For example, if you take two-dimensional quadratic cone, now not three-dimensional but two-dimensional, and now really blow it up at the origin. So again, you glue in P1. Then the whole thing is two-dimensional, but the fiber over this vertex is one-dimensional, so it's semi-small, and everything's fine. And in fact, the push forward in this case will be the constant sheaf on the whole of X plus, but again, in degree -1, plus the delta function and the origin. Okay, and this direct sum business is something not random, and in fact it is maybe a first occurrence of the decomposition theorem of Belenson, Bernstein, Deligne. And it really demonstrates the importance of perverse sheaves. So assume that we have a proper morphism. But now I don't assume that X is smooth anymore or anything at all, just the morphism is proper. And P an irreducible perverse sheaf on X. Then we can take the direct image, the full direct image in the derived category, and it's the same as a Schritt push forward because it's proper. And now it's some object of derived category on Y, so it's a complex of sheaves. But the fact is that this is the direct sum with cohomology. And each perverse cohomology is semi-simple, that is direct sum of irreducible perverse sheaves. But if you view it from the point of view of usual cohomology, like you take the usual. So it will be a usual constructible sheaf, but then it just doesn't even make sense to speak of its reducibility because there are no irreducible or semi-simple constructible sheaves. So it makes no sense to talk of semi-simplicity. But at least this complex of constructible sheaves will not be the direct sum of its cohomology. So it is the direct sum of its perverse cohomology, but not direct sum of its usual cohomology. And in this sense, perverse sheaves are much better than the usual constructible sheaves. Okay. Now this theorem is absolutely fantastic. First of all, its proof is really difficult. So it depends on Weak conjectures, as explained by Vadim Bologotsky last year, but in fact much more than what he explained. He explained only this for cohomology with coefficients and constant sheaf, that is the usual cohomology of varieties over finite fields. But here in cohomology with abstract coefficients, arbitrary constructible coefficients. So it's in another paper of Delin, Weak conjecture 2. And it took Delin maybe 7 years to write this second part after the first part of the proof, for which he received the Fields Prize. So it's really very deep. So the total proof maybe takes like 1,000 pages. I don't know. I mean, from scratch. So it's really deep. Also, what is curious is that we only speak of sheaves over complex varieties with complex coefficients. On the other hand, I have just referred to Weak conjectures about varieties over finite fields with L-adic coefficients. So even this transition is not clear at all. How to move from finite fields to complex varieties. And finally, the use of this theorem is absolutely ubiquitous. For example, Lustig once claimed that if there was a notion of copyright or patent pending in mathematics, then certainly all the authors would be multimillionaires. So just everybody uses this theory. So if everybody had to prove just 1 cent for using this theory, they still would be multimillionaires. Okay. So, pardon me?
Когда было бы еще видеть четвертого,
Yeah. In fact, now in the next edition, it's also the fourth author Gagber, and in fact, Gagber was at the time of this writing. Like this, a student of Delin, or maybe postdoc of Delin, and he proved this theorem, decomposition theorem, and many other theorems in this book. But then he was not somehow satisfied with the outcome, because Belenson proved this theorem is much shorter and better and cleaner. And so they wrote down Belenson's proof, not Gagber's proof. And Gagber was not satisfied by this, and he refused to co-sign it. But then, 2 years ago, they published a second edition of this asterisk, and Gagber finally agreed to co-sign it, only if he would be allowed to correct all the typos. And so there is a separate list of typos, maybe like 5 pages long. So he corrects all the commas and all the quotation marks, all the typos. Yeah. Okay. So so we will be using this theorem also all the time. Maybe the first thing I have to do is, I'm sick and tired of writing this. Maybe I will only write this from now on. Okay. So we'll also use the following immediate lemma. Mm, so I have a variety x and a point, and the closed embedding of this point, and we have an irreducible perverse sheaf. On x, and then we restrict it to this point in two ways. We can restrict it by the Schrieg, and we can restrict it by star. And since they are adjoint of the push forward, of the same push forward, there is a canonical morphism like this. Also because this is just the cohomology with support, and these are all cohomology, there is a canonical morphism like this, but I claim that it is zero. Unless this perverse sheaf is just the skyscraper sheaf at this point. Okay, and this is absolutely obvious because of the definition of reducible sheaves I gave right here. So if this P is not delta function at this point, well, it might live away from this point at all, then there is nothing to prove. But if the support contains this small x, then the dimension of support P is at least 1, and hence implies that the pullback lives in cohomological degrees less than 0, and the Schrieg pullback lives in cohomological degrees bigger than 0. Okay, and so there is no such morphism. Okay, and one more lemma. So, as you might notice, we're now getting back to our geometric situation. So if you remember, we had the Springer resolution, and inside we had the fixed points of some element with dilations, and resolution like that. So we will be mainly concerned with this from now on. And in terms of this, I formulated some construction of modules over the specialized affine Hecke algebra, and I claim that there was a map from substandard to costandard. The image was irreducible, and now we're going to prove this, hopefully today, using the machinery of perverse sheaves and this decomposition theorem. So my x, what was this? And my point was essentially 0. Okay, and now the next.
Sorry, I forgot what is n alpha.
This is A, yeah, and A was an element ST in G cross C star. So it acts on the nilpotent cone just by conjugation and dilation, and this is the fixed point. The fixed point set. But do I understand correctly that this is Roma-Gonin?
Yes.
Oh, thanks. Because I had hallucinations that I always hear your voice, but then maybe I am wrong. Okay. So the next lemma says that suppose you have a smooth variety M, so it will be like this, and a proper morphism to N, it will be like that, morphism mu, so it's proper. But not necessarily, they're not necessarily of the same dimension. And you see, for A equals identity, these two are of the same dimension, but for arbitrary A, by no means. Yeah, there is no need to be of the same dimension. It's maybe very small. Okay, so we have this, and again we have a point in here. So then the Barrel-Moore homology of the fiber is canonically isomorphic to the cohomology. Small m is dimension of this big variety M, M minus this of the crosstalk of the push forward, and similarly the cohomology of the fiber is canonically isomorphic to the cohomology of the stock. Okay?
Usual cohomology, not
Pardon me?
Usual cohomology.
Yeah, this is just usual cohomology, and in fact, what else could you take? Even here or here? Where?
On the right.
On the right. It's just a great vector space. You see, this is some complex of sheaves on N, right? Then you restrict it to the point. You obtain just a graded vector space. Nothing else. You can take only cohomology, nothing else. And here, it's some singular variety in general, and you indeed take its usual cohomology. And this is Barrel-Moore homology. Let's prove it. Maybe just A and B is absolutely the same. So the Barrel-Moore homology, by the scientific definition, is cohomology with coefficients in dualizing sheaf. But we know that this dualizing sheaf, since M is smooth of dimension M, then this is the constant sheaf on M, shift to the homological degree negative twice dimension M. So it's this perverse sheaf shift to the degree negative dimension of M. Yeah, because this is our convention. Okay, but what do we know from this is that the Barrel-Moore homology of the fiber, but by definition this is the cohomology with coefficients in the dualizing sheaf. But we just take the opposite degree, but this is by definition. So what do we get? Okay, now by its change, this is cohomology of the push forward of the restriction, Schrick restriction to the fiber. Okay, and this is the cohomology of the push forward, recede to the point, and this is just what we wanted. Okay, so this M just comes from this sheet. Okay. Pardon me? Here? Because well, this is the fact of life. The dualizing sheaf is the sheaf of orientations, but any complex variety is orientable of twice this real dimension.
Вот снизу написано, что взяли щипчок, это самое, что Schlicklich extension, Finkelberg.
This?
Да.
Yeah, again, if you want this, so you have the fiber, it embeds into M itself, and this projects to point. And then we know that, well, there is a composite projection, maybe it's called PR. So we know that the dualizing sheaf of this is of the constant sheaf on a point, and then you can decompose it into this. Is it okay? Yeah. Is that we have the following commutative diagram. So this is the same as cohomology. I will just rewrite it once again. But this is the same as cohomology of the Stokes star. Okay. And this is the same as cohomology of the dualizing sheaf. And that is the same as cohomology of this. And finally, this is the same as homology of the fiber. This is the same as cohomology of the fiber.
Миша,
Yes,
сейчас, может, я
and the diagram commute.
чего-то
Yes,
понимаю, а левые 4 члена,
these.
в смысле, у тебя сверху написаны два одинаковых.
Here.
Да.
Yeah, just
Единство.
well, I can. Sorry. Yeah, why do I do this? I'm sorry. Maybe.
Вроде бы.
Yeah, sorry. I just copied. Sorry.
Да.
Sorry.
Ага.
Okay. So here I have defined this morphism particle. So how does it come? So you start from a Borel-Moore homology of the fiber, then you just take the push forward and get into Borel-Moore homology of the ambient space. And now it's smooth, so by Poincare duality, this is the same as cohomology of the ambient space, and then you can take restriction with respect to the embedding of the fiber, like this. Okay, so this is the vertical morphism nu, and now if you take a contractible neighborhood, so somehow this takes care of standard modules, and now somehow dually I wanna express the co-standard modules in terms of some Shrikology, some sheaves. Okay, so if you remember when we defined the co-standard models like 3 weeks ago, we took not the cohomology of the fiber, but of some tubular neighborhood of this fiber. So that's what we are going to do now. So we take some neighborhood. And you tilde its pre-image upstairs in M. So it's a tubular neighborhood. Of MX, the fiber. Yes?
А в каком смысле мы сейчас разработали стандартным модуле?
Well, I will formulate the claim maybe in 10 minutes. But
И я прошу прощения.
Yes.
Сейчас, в стандартном модуле нам была история, что мы рассматривали, я ведь не ошибаюсь, что мы рассматривали
Пространство кратности, да?
Absolutely, yeah.
И это не исключено.
Absolutely, yes. And also we will need some local systems, and so far there is no local system. We just consider, so to say, one point stratum, like here, point 0. Okay, so if I want to take the cohomology of the stock of the pushed forward, then it's the same as cohomology of this contractible open neighborhood, and this is the same as cohomology of its pre-image with coefficients in the constant sheaf with the shift, and this is the same as just shifted cohomology of this tubular neighborhood upstairs, and also we know that the cohomology of the tubular neighborhood are the same as cohomology of the fiber, because it's tubular neighborhood and the fiber is its homotopy retract. And finally, the homology, Barrel-Moore homology of the fiber are the same as the ordinary homology of the tubular neighborhood. And in fact, there's a useful observation anyway. Yeah? If you have some singular compact space, then its Barrel-Moore homology is the same as the ordinary homology of a smooth space that is retracted onto our singular space. Why is this? That's because the Barrel-Moore homology of the fiber is dual, just by definition, of the cohomology with compact support of the fiber. Now, the fiber was compact, so it's the same as cohomology without supports of the fiber, and this is the same as cohomology of the tubular neighborhood, and the usual homology are also dual to the same thing. Okay, and now we can extend this diagram to the right a little bit. Okay, so there's again Poincare duality equal to m plus something, cohomology of the tubular neighborhood modulo tubular neighborhood without the fiber, and but by the inverse to the restriction morphism, this is the same as the cohomology of the tubular neighborhood, and then we can return back. I mean, here you have a natural morphism, just for forgetting the boundary. Well, not the boundary, but this complement to the boundary. Again, back from Barrel-Moore homology of the fiber, and here we by Poincare get the homology of U tilde, this tubular neighborhood, and here we have the push forward embedding, and finally this is the same as the ordinary homology of the tubular neighborhood, and this is the same as Barrel-Moore homology of the same tubular neighborhood, and this is the canonical morphism from the ordinary homology to Barrel-Moore homology. So this is the dual to the cohomology with compact support, morphism from U tilde to cohomology without complex support. Yeah, the ordinary homology is dual to this, and the Barrel-Moore homology is dual to a compactly supported cohomology. Okay, and now we're almost done. Just let me say that by the decomposition theorem, we have the push forward of the constant perverse sheaf is the right sum. Yes. I will just say in 1 minute what we were proving. I will formulate the claim in 1 minute, but I need to introduce some notation. Okay. So it's the direct sum over various irreducible perverse sheaves. So now what is phi? Phi is the collection of strata and local systems, irreducible local systems. So if you remember, any irreducible perverse sheaf is Goretzky-McPherson extension from some local system from some stratum. Okay, so this is some general nonsense, and these are multiplicity spaces.
Это бета, это финиш.
So phi is the numbering of summons, and each summon is a certain stratum and a certain irreducible local system on this stratum. Sorry. Sorry, yeah.
Страта получается теперь. Миша, можно
Yes.
Она приводит, там такие гемологии стоят у стилей, обычные, Баррел-Мур,
Here.
Да, что это?
Barrel-Moore homology. So if I wanna use the ordinary homology, I write ordinary. If I write this, then by default this is Barrel-Moore homology. Okay. So this is a great vector space. So L phi is direct sum over I, L phi of I. Okay, but this grading we will often ignore. So we'll forget about this often. By definition, it is graded because these irreducible sheaves occur in various homological degrees. But we will mainly ignore this fact. So it does have some meaning with respect to Janssen filtration and so on, but maybe we'll not go into Janssen filtration here. Okay, so this grading will be mostly ignored. For example, if you consider, say, a point in 0, in A3, and then you take blow up at 0, yes, and you take this irreducible perverse sheaf on the blow up, and take its direct image, then you will certainly have the constant sheaf, perverse sheaf, on the whole of A3, but you will also have a lot at the origin, right? Because you glue in P2, and P2 has three-dimensional cohomology in degrees 0, 2, and 4. But if you somehow perverse normalize it, it will be in degrees -2, 0, and +2. And so what you get is this plus the delta function at the origin with some multiplicity space, L0. And this L0 will be just one-dimensional in degree negative 2 plus in degree 2. Okay? But if we disregard those cohomological degrees, this will be just two-dimensional vector space. And we will often disregard cohomological degrees. Okay? Altan, you are not happy because I forgot the middle summon, right?
Нет, ну, наверное, он уже...
Because it's in here, right? Yeah.
Здесь две прямых скобочек, прямоугольных скобочек, а сверху круглых скобочек. Что это значит?
So this is L0 of probably negative 2, and this is L0 of 2. This is notation for cohomological shift.
Yes.
And this is notation for the corresponding multiplicity space.
Yes.
I don't want to take something and shift it. It is just some multiplicity space.
Вот, то есть ты ничего не подкручиваешь, это просто обозначение, как индекс.
Yeah, yes, because it's graded space, so it's a sum with graded components. It's the notation for a graded component of this graded vector space. Okay. So what did I want to say? I wanted to say that the cohomology of the fiber equals the direct sum over this of the multiplicity spaces tensor cohomology of the stocks of those IC sheaves. Okay? Just from this decomposition, yeah, I see that I can decompose the cohomology of the fiber according to this direct sum. And now, if my irreducible sheaf happens to be the skyscraper at this point, yeah. So there are various summons, but among them, it may happen that we have the skyscrapers somewhere, in particular at this point X of interest. Then we see that the corresponding multiplicity space Lx, is by definition Lx, it enters in this decomposition with the multiplicity that is cohomology of this thing. But the cohomology of this thing is just one-dimensional, right? Because the delta function you just restricted to x itself, it's again delta function. Take cohomology, it's again one-dimensional space. Enters with multiplicity cohomology of restriction delta x. This is just C itself. So somehow it enters just as it is. And finally we see that this multiplicity space just lies inside the Borel-Moore homology of the tubular neighborhood. Okay? So all the other, in principle, enter with some multiplicities that are equal to the stocks of corresponding IC sheaves. But this particular one enters just with multiplicity 1, so it just lies there as it is. Okay, and finally we we can satisfy the popular demands and formulate the proposition why the hell we did all this nonsense. So now I claim that the image of the push forward, the embedding of the fiber from homology of the fiber to the homology of its tubular neighborhood is exactly this multiplicity space. Okay, and second, that the kernel of this embedding morphism, push forward, equals the kernel of the bilinear pairing from homology of the fiber to complex numbers. So it's just denoted like this, and it is just the intersection pairing in the ambient space. Like this. Yeah, so when we formulated some list of basic properties of Borel-Moore homology, we in particular had such things, and here we use them. I mean, the ambient's tubular neighborhood is smooth, so that there is a notion of intersection pairing, and you see they have complementary dimensions, unless. Yeah, they do have complementary dimensions. So the pairing goes to H 2m of U tilde. That is just complex numbers. Okay. Or maybe I'm wrong again. Just H2 to H0. But sorry. Okay, so if I'm in Borel-Moore homology, it is 2m. But somehow dually, if I think of ordinary homology, it's just intersection of cycles. And then I go to the ordinary homology in degree 0. Okay. Okay. Pardon me? So it's 2m? So I first push forward to U tilde, and there I just take the intersection pairing. So I just take the intersection pairing, but it does not make sense to take intersection pairing in the singular fiber. It only makes sense to do this in the ambient smooth space. and I do it there. Okay, so let's prove it. First, we identify this push forward. With sorry, with this. I'm sure you noticed. Okay. And decompose it into the direct sum over phi. The multiplicity space L pi tensor cohomology of the Schrieg pullback of the corresponding irreducible sheaf into cohomology of the usual stock of the IC sheaf. Okay, and note that by the first lemma today, the image is not zero, only for IC thickness, just delta x, the skyscraper x. Okay? For all the other summands, the image is just zero, as we argued earlier, and so they do not contribute to the image. Okay, so the image comes only from the skyscraper contribution. Now, as for the second point, we identify this push forward with that. And the pairing, this bilinear pairing, we identify with the following composition. So we have the ordinary homology of U tilde times the ordinary homology of this tubular neighborhood, and there is this usual intersection of cycles pairing to the 0 degree ordinary homology. That is just complex numbers. And here you have the morphism that is just identity in this factor times canonical morphism along the second factor to the ordinary homology, which is the degree of the tubular neighborhood times the Borel-Moore homology of the tubular neighborhood. Okay, and here we have also the sort of intersection pairing to the ordinary homology zero, let's say complex numbers, and this is just this smooth variety, so it's Poincare dual to the action of usual cohomology or the completely supported cohomology of this tubular neighborhood. Again, by Poincare duality, this pairing is non-degenerate. So the bottom is non-degenerate. By Poincare. Since the tubular neighborhood utility is smooth. Okay, so this means that the kernel of this pairing is equal to the kernel of this canonical morphism. Okay, and that's what we actually claim. So there we are. Okay, and now I can erase this long diagram. But maybe not the proposition. First of all, the corollary from this proposition is that the push forward under the embedding of the fiber gives rise to an isomorphism from the cohomology, homology of the fiber modulo the radical of this pairing and the multiplicity space Lx. So this was the standard module, if you remember, and this will later on, maybe already not today, but eventually next time, in the beginning of next time, we'll see that this is the reducible module. So the multiplicity space realizes an irreducible module over the specialized affine Hecke algebra. Okay, this was all about the situation when X in N was the smallest stratum. Okay. Now, in general, for other strata, we assume or use, when we use that all the strata are orbits like O of some group action. So I mean, in our basic situation, when n would be this fixed point set in the point cone, then the group we'll use will be the stabilizer in G of, or maybe in this standard group of A. Okay, it will act on the fixed point set, and it will have finitely many orbits. We discussed this, and we'll discuss it more, hopefully, or maybe in the next life. But anyway, this will be our group, and it will have finitely many orbits. That will be our strata, the stabilizer. So X will be a point in this orbit. There will be this stabilizer of X in this group. I don't know, let's call it GX with component group. CX. Just, I mean, like this. So all the local systems in question will be equivariant with respect to this. So they will actually come from representations of this finite component group. So the parameter of irreducible Garesky-Macpherson sheaf will be just a pair in orbit and chi. So chi will be an irreducible representation of this component group. Okay, and so the corresponding multiplicity space will be equal to the image of Brown-Moore homology of the fiber over this point of our orbit, but we have to take into account our local system somehow. So this fiber will be acted upon by this stabilizer group, and its homology will be acted upon by the component group. And so we can take the atypical component corresponding to this irreducible representation chi, and we'll take the image of map to the homology of certain sort of U tilde, but now maybe let me denote it by S tilde rather. And again, I take the chi as a typical component. So S tilde will be the pre-image of a slice to the orbit through my orbit X. And yes.
Сейчас рассматриваем общую ситуацию, в частности, учитываем локальную систему.
Yes. Yes.
А где, когда берем типическое?
Exactly. Yes. We'll take care of all the possible equivariant local systems by taking the atypical component.
Все прекрасно.
But the subtle point is that certainly when you just dissect this global situation by a slice, you will get back to the previous situation when there is some smaller stratification induced on this section on this slice, and the smaller stratum corresponding to this orbit O will be just the point X. That's all fine, but the slices we talked about a few times ago were some local analytic slices. And in this local analytic situation, the decomposition theorem does not apply. It has some algebraic origin, or even arithmetic origin, with the conjectures needed to prove it. The thing that somehow saves the day is that in this case there are sort of Slodovy slices that are global. So it is possible in our particular situation to choose this slice globally. So it will be really an algebraic slice, not an analytic slice. So we can reduce to the above situation of stratum. There is a global slice. Okay. And well, maybe let me continue that this is also isomorphic to
Миша,
yes.
Нас не спас какой-нибудь слайс Луны или что-нибудь?
Maybe also, yeah. Maybe let me write that, yes. Or more generally. Luna, slice. Okay. So this is the first modular radical again of intersection form with isotopic component taken. Okay, so let me say some last words for today. So we apply this machinery to the case when M is the fixed point set in the Springer resolution and is the fixed point set in the nilpotent cone itself. So mu is the restriction of Springer resolution map. And so we get some sheaf theoretic interpretation of what we had before. So L, we had this notation AX chi, and it was the image of Borel-Moore homology of the fixed point set. So this A was a semi-simple element in group G and a parameter in multiplier group that was assumed not out of unity, and then X was an important element in this fixed point set. Okay, and this was the fixed point in the flag variety. So well, maybe if you look up what we had 3 times ago, you find this notation, and then we take the chi isotopic component, and this was denoted by the standard model K A X chi, and there was the nature back to the cohomology of the preimage of slice isotopic component, and this is also denoted by K dual A X chi. Okay, and the image of this once again the image of this, yes, it was LAX chi, but just by definition, 3 times ago. But what do we get now? That this is equal to the multiplicity space of the corresponding IC sheaf. Okay, and this is equal to the homology of this fiber in the flag variety as to the component model of the radical of the bilinear form. Okay. Okay. So once again, this would be irreducible module over the affine Hecke algebra is the multiplicity space of the corresponding IC sheaf in the direct image of constant sheaf on this big smooth space. Okay, let me just formulate the next important claim, and we'll prove it next time. I mean, from this claim, it will immediately follow that those L's here, this or that, they are really irreducible representations of the affine Hecke algebra. So the Borel-Moore homology of this local space, maybe denoted by Z. I forgot, but anyway, this was the Cartesian product of Cartesian square of n tilde over NA. And this was in fact our specialized integral. Okay. So the claim is that this is isomorphic to the X algebra in the derived category of constructible sheaves on NA from the push forward of C constant sheaf on this M. Fixed point set in the cotangent bundle of the variety. Okay, so this X from one direct image to another direct image, or to itself, in fact. So it's an algebra under composition. And this algebra is isomorphic to that algebra. In fact, this algebra is also graded, as you see. Oh, sorry, it was Borel-Moore homology. I'm sorry. This is graded. This isomorphism does not respect gradings, but it doesn't matter. So even with gradings disregarded, it's enough. I mean, for this algebra, it's easy to classify all the reducibles, and then it follows that the reducibles over this algebra are just those multiplicity spaces. So thank you for today.
So you got an additional grading on this?
There are some additional gradings, but at our level of understanding that they are not very important. So they are related to some Janssen filtration, but this will come later.
Это факт не зависит от нашей специфики, да?
Yeah, but this is something very general. Yes.
Да,
Absolutely. Yeah. So you might forget about this. This is very, very general.